Good afternoon. My name is Paul Sears, and I'm a solutions architect with AWS on the partner organization. I support big data partners. And today I'm joined with Alex Fan, who's the lead architect at Experian. And we're going to be basically listening or learning about how Experian leverages Amazon EC2, Amazon S3, Amazon EBS with Cloudera Hadoop and for their big data analytics. I'm also going to do a little bit of a talk around EBS itself and kind of give you a little preview on Hadoop. So let's go ahead and get started. There we go. So under big data analytics, we have about 5 general workload categories. And if you were using Amazon services, Amazon EMR, Redshift, Kinesis, or DynamoDB, for example, you don't need to worry too much about managing your big data solutions in terms of your storage and your capacity as is all managed for you. But for today, we're going to be focusing more on Cloudera and doing Cloudera on EC2. So we'll learn about how to optimize your storage, choose the right instance types and the right volume types for your storage for Cloudera. So back in when Hadoop was first came around, the idea was that we had a lot of expensive network storage and a very expensive direct attached storage, EBS SANs, and a lot of expensive servers. So in order to do big data where storage was expensive, Hadoop was designed with a file system in mind that leveraged commodity hardware, commodity disks. So it was very inexpensive. And they replicated the disks and servers multiple times to give you better durability, better availability of your services. But when we look in the cloud, it actually all changes because with EBS being durable and persistent, we can take some advantages that we didn't have before. So we have basically network attached storage, but allows you to decouple your compute from the storage, allows you to scale each component as needed for your big data solution and optimize your costs while you're doing it. We also offer an instance store, which is ephemeral storage for certain use cases as well. So to remind you of some of the building blocks we have with our storage services, we have our object storage, which is Amazon S3, Amazon Glacier. This provides 11 nines of durability, and it's basically around file objects. We also have Amazon EFS, which is our highly scalable and available elastic file service, which is basically NFS that's being served for you, fully managed solution. And then we have block storage, which is the raw disks you would normally see on a server, and we're going to be focusing on that today with Amazon EBS. So we have 2 kinds of block storage offerings. You'll get ephemeral or instant store with EC2, which is the actual storage that's attached to the physical hosts that your instance run on. And these come in either SDD or HDD offerings. We have EBS SSD back volumes, and these come in GP2 and IO1 offerings. And then we have EBS HDD back volumes, which come in ST1 and SC1 volumes. So Amazon EC2 Instance Store, as I mentioned earlier, is non-persistent. It's ephemeral. It's local to the host. Is where your instance is running. So the data isn't persistent. If you terminate your instance or there's an issue with the host, that data is no longer available, so you lose that data. The data is not replicated anywhere, so it's basically what you have on that host itself. There's no concept of snapshots, so if you want to copy data, you're doing all those operations manually. You can get instance store in either SSD or HDD instance types. And so now what is EBS? EBS is our block storage as a service. It offers 5 nines of availability, and there's an API that allows you to create your volumes, and then you can attach and detach your volumes to your EC2 instances. And we'll see how this flexibility can really be an advantage for how you design your big data applications. This is a network-attached storage through where you connect those volumes to your instance. However, you're not getting a dedicated disk. You're getting a portion of volumes comprised of many, many disks that are shared. So, as we mentioned, the volumes persist independent of EC2. You can detach and reattach as you need to. You can separate your compute from your storage. So if you're using ephemeral storage, instance stores, you're very limited in how you can scale your storage. There's a finite capacity on those instance sizes. And if you want to add more storage, you need to add more instances. With EBS, you can actually just scale appropriately. You can add more volumes and attach them to your instance as you need to. You can attach and detach between instances within an availability zone, so you actually can take an instance down or detach your volumes, shut an instance down, make a new one, and reattach your volumes. This allows you to play around, experiment, allows you to right-size the instance for your needs. So if you need more compute, you can change your instance size and then reattach your volumes. And it's shown here basically how you reattach from one to another. And it really is that simple. So we have many offerings of volumes, how do you really choose, make the right decision what you're going to use? So in general, my animation is gone. So in general, GP2 is the volume that's our general purpose. It works for most use cases. It supports random I/O. It works well with sequential I/O. It's the general volume. So if you really don't care what volume you want to use, GP2 is a good choice. If you have a need for a dedicated, consistent latency and higher IOPS, then you can use IO1, and this will give you a higher consistent latency and up to a lot higher IOPS. If you really need an extreme amount of IOPS, you can use I instances, i3 for example, which have NVMe SSDs, and you can get to 3 million IOPS. But again, that's going to be ephemeral or temporary storage. It won't be anything permanent. If you're looking at throughput and costs are a consideration, then you can use our HDD volumes, which will be like SC1 or ST1. SC1 is a little lower throughput than our ST1 volumes, and so you can balance your costs and performance with that. And then we also have a instance store, ephemeral type, with a D2 as well. So EBS also offers encryption, and this it's actually very simple to use. You just enable it when you're creating your volume. It's that simple to do. You can encrypt you can actually attach both encrypted and decrypted volumes to any of your instances as you need, and there's no performance impact at all using encryption for this. And when you make snapshots of these volumes, they're also encrypted as well. Oh, my animation is a little off here, sorry. Okay, so we also have the concept of EBS optimized instances, and this is where if you normally would use EBS on certain instances, the bandwidth to talk to the storage is also shared with the bandwidth to do everything else. So it's a shared bandwidth. In this example here, C32X large has 125 megabits of bandwidth that's shared between EBS and your other services, like your other network services. S3, other instances, the databases and such. So when you have an optimized instance, for example, you can actually dedicate, or in this case, you can enable EBS optimized, and it gives you a dedicated set of bandwidth for your storage that is separate from the rest of your network. So you get better performance, better throughput without sharing that bandwidth with other network services. So it's an EBS optimized is now enabled by default on most of our newer instance types, such as the C4 and C5 instance family. And also, when it's enabled by default, there's no additional cost. You just get it. There are some instances where it's not enabled by default, but you can enable it, and there's a little bit of extra cost for that, but you do get dedicated bandwidth in those situations. There are also some instance types that do not support it right now, such as a C3 8x large. And my animation again. Okay, so we're going to get into a little bit of Hadoop here. This is kind of giving you a background for what we're going to be learning with experience with big data analytics. And Hadoop uses an HDFS file system that is very sequential I/O based. It does read and write to sequential in 64 megabytes or larger blocks. It doesn't do any random I/O in terms of the actual file system itself. It replicates the data 3 times by default, so you have 3 copies of your data across your Hadoop cluster. So you can also layer different file systems and make them compatible with HDFS by using an API calls. For example, with EMRFS, which is the file system we use with Amazon EMR, it uses an API call to translate, or it builds a bridge between Amazon S3 API calls and Hadoop HDFS API calls. So we actually can run Amazon EMR on S3. So with Amazon S3, HDFS might be a good choice to run on S3, and there's some advantages with that. For example, you can scale out horizontally without any data distribution. You can just keep growing your data and keep growing your clusters without having to do anything because the data is all available automatically for you. There's no need to do any disaster recovery because Amazon S3 is extremely durable with 11 nines of durability. So you don't need to have multiple copies around. You still should have probably 2, but you don't need to do snapshots or backups or those kind of things for a availability aspect. You may still want to do that for data integrity. And you also can use transient clusters now if you're using S3, so you can actually have clusters that you run only when you want to do your analysis or run your jobs, and then you can turn them off, and your data is still available in Amazon S3 for other applications or consumers. But there are some disadvantages as well. Amazon S3, it doesn't support immediate consistency, so you have some consistency issues. For example, if you do a rename operation on HDFS, you're renaming the actual data structure, the node name inside HDFS, and it happens in place. With Amazon S3, it's going to be a copy command. It's going to copy the data from one file to another to do the rename, so it's eventually consistent. There are some mechanisms in place to address this. The latest Apache Hadoop previews and support of S3 and S3A, S3 Guard kind of address some of these consistency issues. Amazon EMRFS will use DynamoDB in the back end to do metadata, keep track of metadata so they can keep track of consistency issues for you. Security has various amounts of support right now. It's getting better all the time. And there may be some compatibility issues with some certain distributions or certain engines that you might be using. So when should you use HDFS on EBS? Really comes down to when you want really high IOPS and high performance. So EBS is going to be much more performant for your storage than using Amazon S3. If you have long-running clusters, for example, if you're running a MapR distribution, you're running a MapRFS, and you have a global namespace, those clusters are always going to run. So in that case, running on EBS makes a lot of sense. If you're doing your own distribution, like we're discussing Cloudera here, Hortonworks, or MapR, then you would probably want to use HDFS on EBS. So if you're using HDFS on EBS, you can actually optimize your choice of storage depending on the nature of your cluster and how you're handling your jobs and how you're processing things. So you have a choice of Amazon EC2 Instance Store, which is the ephemeral storage. And a D2 instance can get about 3 gigabytes a second of throughput overall, but your limitation is really more the network and compute than it is going to be the actual instance storage size. So it's very common that you need to scale your compute higher to get the throughput. So in this case, Amazon EBS ST1 volumes are a really good choice for Hadoop clusters because of the sequential I/O and the throughput up to 500 megabytes per second with burst, and the baseline of 40 megabytes works very well for Hadoop workloads. Recommending that you use at least 2 terabyte volume sizes to get the most out of your buckets and your burst performance. And also because Amazon EBS replicates automatically within the availability zone, you can reduce your replication factor in Hadoop from 3 to 2. 3 is the default, and you can actually save some storage costs as well because you don't need to have the extra data around for that durability. Okay, so now we're going to be moving into Experian story, and I'm going to turn over to Alex, who's going to share his experiences. There you go.
Thanks, Paul, for that terrific overview. So I'm Alex Vaughn. I'm the architect for the Advanced Tech Group at Experian. I come to Experian from Cloudera, where I deployed CDH on Isilon, on VMware EXI, bare metal, AWS. So to give you some context of what we're doing at Experian, we have a large legacy infrastructure, DB2, mainframe, lots of data, a mountain of data. And what we've done is we've built an analytical platform to sort of prove out the migration into the cloud. That's the analytical sandbox that I'll be talking about. It's basically a hybrid cloud platform, and in its long-term future, it'll be integrating batch and real-time data. We've done this for about a year only, a little over a year. We have 3 CDH clusters, 800 terabytes of EBS ST1, 1.1 petabytes of S3, and it's probably going to double in the next less than a year, and 70 terabytes of EBS GPT. Those numbers are actually kind of indicative of this entire talk of how we use storage. So how did we manage to go into the cloud? Well, this is a diagram that shows a very rough idea of the architecture, the data flow. The bottom box is our data centers, one of our data centers. Our customers go through a Citrix cluster, and everything goes through a VPN. We're replacing that eventually with Direct Connect for performance and whatnot. And the data itself gets exported from mainframe, DB2, depersonalized, and everything gets stored in S3 initially, and then processed and stored in EBS and back to S3. So that's the general data flow. We only use PCI DSS services. That's extremely important for our internal security governance. The ones in green are the ones that are very important to us. You can see EMR there. It's also, we do a lot of processing with EMR. Because EMR has the S3 file system, which avoids the eventual consistency issue. Okay, so what's S3? What can I say about S3? It's everywhere, right? Like you feel it, like when you go to work, when you go to church, when you pay your taxes. Remember that? It would be great if Lawrence Fishburne talked about S3. So it's kind of like the Matrix. It's really the backbone for the Ascend and for Experian. There's 11 nines of durability, like Paul said. So it serves as a really good record of store. And if you're using CDH 5, 10, and below, you're going to have problems with S3 if you're doing transactional processing because of the eventual consistency. There's third-party systems like Databricks' DBIO, S3 Guard, which comes from Cloudera CDH 511 plus. So those can be used safely. And EMR, of course, is S3 safe for transactional writes. So the way we also use S3 is that we share data across clusters and across AWS accounts. We use it as a configuration store for initializing our servers, for CloudFormation, SSM, user data, and logs and backup. That's pretty much it. Since this is more like an EBS talk, I'll just leave it at that. What we can do, though, is also enable some S3A optimizations that are available in like more modern versions of CDH. You know, the fast upload is very important. Set that to true, default's false. The maximum number of connections, 1,500 should be a minimum, really. But you can max it out from the total cluster cores. So by default, the fast upload buffer is on disk, which is EBS, which is kind of slow. It's going back and forth in network. So set it as a memory array. And I set the multi-part size to be equivalent to the DFS block size, which should be around 128 megabytes or 256 if you're like, you know, using Impala a lot. And the total amount of buffer size is really a calculation of the multi-part size plus the number of active blocks that are transferring. The block size for our S3 data is I set the same as our HDFS block size. And the S3 endpoint region is very good because all our traffic goes through an S3 endpoint for security. It doesn't leave the VPC. And the threads max should be set to the number of available cores that Yarn can use for that particular node manager, that particular node worker. So how do we plan for high availability? So on a classic bare metal or whatnot, there are three components. One is sort of like the racks, like how you distribute the workers. There's different types of roles. There's the master utility server role, gateway role, worker role. Worker role contains the Impala daemon, the node manager, the data node, which is for the HDFS storage. So we can simulate racks via AZs. So what I show here is that our VPC consists of 5 AZs, and we distribute the cluster across 2 or more AZs. We have a SAS cluster that we distribute the same way. We have Hue instances that are specific for each client, because Hue is kind of a security hole. There's a lot of features that are exposed with Hue. So every this is a multi-tenant cluster. Every client gets its own Hue database. We have RStudio across multiple zones and a Tableau servers as well. Another major component of high availability for Cloudera, for Hadoop in general, is the metadata. That's where Cloudera Manager keeps its data. That's where the Hive metastore is. So your backing database really should be a cluster of some sort. We use RDS. RDS is deployed in a highly available production layout, daily snapshots, whatnot. So with AZs, we have the ability to have rack awareness and placement groups. So just to get into AZs and racks, just to give you more info, the default replication is 3. A file is broken into blocks. You see yellow, green, purple. The first block is written to a rack, whether that rack be a bare metal or an AZ. And the second and third blocks are written to another rack or AZ. And because EBS has 5 nines of availability, remember an EBS volume is not a hard drive; it's a service. And if you recall from the Google study on hard drives, 2% of all drives fail in the first year, 9% fail within 3 years. So this is much better. So what we've done is to reduce costs. We've lowered the default replication to 2, and that's a 33% drop in SD1 storage. So placement groups are also very important. They provide the lowest latency among nodes, highest network throughput. They're essentially a cluster. The only issue is that you've got to sort of pre-plan your cluster, because adding additional nodes within a placement group isn't always guaranteed. So what we do is we actually sort of deploy a pool of worker nodes, more than we need, pretty much all configured, and the lowest possible, the least expensive instance type, which is an M4 large. And when we need it, we bump it up to the size that we need. And I'll get into that in a bit. So some of these placement groups can be enabled for certain EC2 types here, the MCIR XPF series. Smallest type is a large. And really, they do best in 10 gigabit network and higher. So the second part of like deploying a highly available cluster, Hadoop cluster, is of course to distribute the services across the zones. So here we have 2 racks and 2 AZs, and each rack or each AZ contains a pretty much a exact copy of the other rack. You have 2 services. Everything is HA, unless it's Sentry. So CDH 5.13, which was just released about 2-3 weeks ago, closed the single point of failure for Sentry and the Hive Metastore service. There now we can deploy every single service in an HA manner. Things that require memory or name nodes, memory-intensive service roles include name nodes, Hive Server 2, Uzi. So in choosing your instance type, remember to reserve like memory for the system processes as well. That ensures a more stable deployment. So EC2 instance types for a secure Hadoop. In choosing the particular instance types, I go through 4 different parameters: storage, network, whether it's network optimizable, the total memory, and the memory to vCore or core ratio. So we stay away from actual like D2s because everything is AES 256 encrypted. So EBS provides that out of the box. There's EBS optimized instances, and it's flexible, like Paul said, to add and remove drives. So EC2 types that are appropriate for the master utility server role are often compute and memory types. These include the M44XL, C4 extra larges, R42XLs, R44XLs. And you could see some of the specs that I use to consider what's appropriate. The number of cores, the total memory, the throughput of each EC2 type is very important because this isn't a limited, bandwidth that goes through an EC2, there's only so much. The pipe is only so large. So some of these have different types of throughput. And we also associate costs, of course. So if you recall, like a name node for each block, each HDFS block consumes about 300 bytes of data. There's 2 components. There's a file pointer and some other metadata for each block. And that's what the name node keeps in memory. So we usually use like 8 gigabytes of heap for that particular service. And Hive Server 2. Now, in my experience, Hive Server 2, if you're not using G1GC, you're using CMS likely, right? And CMS doesn't work well with heap sizes that are 14 gigs or higher. You just have these stop-of-the-world type of garbage collections. So we've actually converted all our Hive Server instances to use G1GC. That enables us to use heap sizes that are 30, 40, 50 gigs. And Hive Server 2, if you recall, is the proxy for queries. All the SQL that goes through a Hive instance gets pushed through a Hive Server 2. So you can imagine this like cluster where there are a lot of SaaS clients making queries, that could be quite a bottleneck. So what do I mean by memory core ratio? So let's say, for this instance, we want to use an M410XL as a worker node versus an R48XL, right? So you see the memory; they're comparable. The ratio for the number of amount of memory to core, reserving 2 cores for the system would be 4 gigabytes per core for the M410XL, and 7.8 gigabytes per core for the R48XL. And in sort of configuring the Spark yarn executor parameters, it's recommended that if you don't really understand your workload, you use 3 to 5 cores per executor. That would amount to about 12, 16, and 20 gigabytes per executor. And that's actually too small for our type of workload, large, big data type of workloads, like things like HDO, any sort of analysis, machine learning requires. It's much better to use fewer executors with much larger memory. So in R4 8XL, R4 4XL, R4 16XL, those memory to core ratios are linear. In the R4 8XL, we can start off with 4 cores per executor and have an executor of like 31 gigs. That works really well to start off with. So in choosing EC2 type instance types for worker server roles, we can pick between storage roles or memory types. Storage roles are the D2s. Now here really the D2 8XLs in our experience are the only storage optimized EC2 types that we would consider. It's the only one that has 10 gigabit Ethernet. It has 48 terabytes of instance HDD, very fast HDD, but it's ephemeral. So it's not, those drives aren't encrypted. Now if you're using Cloudera Navigator or NavEncrypt, you can use NavEncrypt to LUX encrypt every single one of these volumes. So that's 48 volumes that need to be LUX encrypted. And Cloudera Navigator NavEncrypt actually sort of automates that. There's a ztab file under etc that handles the mounting and decryption of these block devices when the server restarts. But it's very complex to set up. It's very complex to manage. And in some ways, it's too dense because it's ephemeral as well. So mistakes happen. The instance could be stopped. There could be a hardware failure. So we would have to. So when this happens, all that data is lost, and then when it comes back on, there's a replication storm. The blocks have to be replicated across the cluster, so you have reduced performance. So we tend to avoid that sort of ephemeral storage. And we go with the R4, 8XL, 16XLs as the primary worker instances for our production clusters. These are 10 gigabit, 20 gigabit Ethernet, respectively. They exceed throughput, the instance throughput for the D2 8XLs. EBS encryption out of the box, really seamless. This envelope encryption is great with key rotation and whatnot. And you have custom kernel options for the 8XLs and 16XLs as well. And like I said before, great memory to vCore ratio and very flexible storage strategy. What do I mean by that? So as we grow this out, we often need more compute than storage. So we may attach just 2 ST1 volumes as HDFS, and then just later on attach 2 more. And I'll show you why we use those numbers in a second. So if you're ever wondering how, what resources are consumed by Cloudera Manager, you can go to the Host tab and click Resources, and you can see what Cloudera Manager thinks the resources are needed for that particular server role. It really is a function of the service roles that you deployed on that particular EC2. So that's a good way to check things. So the talks really come down to really like R4 instances and EBS ST1 for workers. So here I'm trying to match the volume burst and baseline throughput with the instance type, because only so much information can flow through an EC2. If you have, for instance, 2 terabyte SD1s, you're going to get the full 500 megabytes per second of bursts. But only 2 of those drives will actually, 2 of those drives, active drives, will consume like the entire throughput for that EC2. And so really, the way we size our disks is a function of both complexity and ease of maintenance, but also of capacity. You know, how often are we going to deploy a 50-node cluster where every worker, you know, has only 4 terabytes of SD1 storage? Unlikely. So instead of, like, say, 22 terabyte drives, we will use 4 10 terabyte drives for an R416XL or 2 for an R48XL. And I threw on the D28XL there for comparison. So you see the max throughput for each one. R416XLs are 20 gigabit Ethernet, so that's a function of the network. Everything is pretty much a function of network. And having fewer large SD1 volumes has a benefit for EBS affinity. You know, like I said, I've worked with VMware EXI before, and it just came as a sort of a precognition that would be a good idea. And the EBS team basically said, you know, fewer large drives, much better than, you know, it's also much better for maintenance, right? Who wants to deploy, you know, for a petabyte cluster, that would be, what, 40, like 500 volumes? So like I said, with the R48XLs and 16XLs, we can do some low-level tuning. You know, there's C states. C states are an idle power-saving feature for most current Intel kernels. And for an R416XL, we have, you know, 5 C states: 0, 1, 3, 6, and 7. You can actually cat that on the CIFS to see to verify. And what I've shown there is that for C state 0, there's like 0, of course, 0 microseconds of latency, 2 for C1, 10 for C3, 40 for C6. And C6 seems to be the default idle state. And I'll show you how we can tune that. So under etc boot grub config, you can set Intel idle max C state to equal 1. This means that the kernel will keep the core at C state 1 and no higher. As you can see from the left screen, the default is C6. 95% of all the cores are on this idling system is in C state 6. When you set that state, 95% will be stuck in C state 1, which is, and how does that pertain to performance or EBS performance? So in writing like a 1 gigabyte file to SD1, we're using the same R416XL, same SD1 drive, complete system idle. Like, this is not a node that's being worked on. But default, default C6 state, it takes 2.3728 seconds, you know. And if we set that idle, it'll write it in 2.287 seconds, which is a p-value of 0.002, which is, you know, significant. So there is some performance improvement. Now, some of this stuff is very low level, and the reason why we do this is because as an enterprise, we can't really use the AWS AMI, and that is something, you know, if you can get away with it, you should look into. A lot of this stuff is already baked into that AMI. So another thing we could do is set the read-ahead buffer. Now, this read-ahead buffer, so the read-ahead buffer allows us to write sequential workloads, have better disk performance and throughput on sequential workloads. It's very important that you verify that your workload is sequential and that you're writing large files, because changing this from default will actually negatively impact your performance otherwise. So the recommended RAA buffer is 1 megabyte. So you would set, you know, RAA to 2048 KB and times, 2048 bytes times the 512 byte sector equals 1 megabyte. So I've actually changed this to 8192 for our R416XLs, and it's something you can play with, and it's very good that when you make these changes, you really should just test it, and it's very workload dependent. So that's very much an Experian setting. But in general, for sequential I/O, a 1 megabyte RA should be sufficient. We also changed it to deadline, the deadline I/O schedule. By default, it's CFQ. And there's a lot of things you could do with CFQ, but intuition tells me deadline is better, mainly because it prioritizes reads over writes. Reads tend to block, it batches I/O, and latency is important for us. So I used FIO to benchmark EBS performance. Here's an example of a file. It's very easy to use. This writes a 1 gigabyte file, and I use this to test some settings that I'll show you in a second. So how does a 410 terabyte SD1 on a R416XL, how does it perform? So if we set the file job to run four reads versus 4 writes, you can see the aggregate throughput for each one. The 1783 is actually very important because that shows you that it maxes out the EC2 throughput. But really, often the workload is mixed. You get mixed reads and mixed writes. So you can set the file config to do that, where 2 disks are writing, 2 disks are reading, and you can see the throughput there. It seems like, the aggregate throughput is much higher, like, 700 times 1500. Plus 1500 is like 2000, but the entire workload takes longer to run by about a couple hundred milliseconds. That goes to show you that we actually never, that's a really important point. We don't exceed the EC2 throughput no matter what. Like I could put 10 terabyte SD1s here on this particular EC2, and we wouldn't get more than 1700 megabytes per second. Okay. So we also use a hybrid EBS layout. Now this is very different than, say, bare metal, where in bare metal we have 1 disk and it holds HDFS, it holds Yarn local data, Hive local data, Impala local data. So what I did here was we have a GP2 boot volume encrypted. We have a data volume that's GP2 where we add the Zookeeper data. We separate Zookeeper logs from Zookeeper data, so we're basically bifurcating that flow for max performance of Zookeeper. Yarn local data is kept on the SSD GP2 volume, Hive local data as well, and the Cloudera Manager hosts and service data. Those used to be in a database, if you recall, but now they're just written to log files directly on disk. So those are those are random read-write workloads. So they go well with ST1. Some of the other use cases we have for our SaaS Foundation server, we use i3-16XLs. With ephemeral storage, that's the recommended. Using ephemeral storage is recommended by SaaS. So we use LVM and stripe those 2 terabyte drives to make 1 16 terabyte workspace, SaaS workspace for ephemeral SaaS data. And SD1 drives for SaaS data, for the persistent data. Okay. So how does SD1 work with, like I said, SD1 should be matched. So you should use the EBS storage types that match your particular workload. Here, files, I show performance or throughput of certain file sizes on ST1. So you can use DD or you can use file, and they both give similar results. So for writing 1 KB size files, the bandwidth is like 2 to 10 megabytes per second, where a Hadoop workload is 64 megabytes or higher. And once you hit around 16, you can realize the full potential of the SD1 drive. And there, we're exceeding the 400 megabytes per second because we're basically using some of the burst rates. So is my assumption correct for splitting or putting the Yarn local data onto GP2? Well, if you look at the Yarn local data files, on one particular node that I just picked out at random, you can see that So the yarn node manager.localsdir is the parameter in Hadoop that specifies where yarn keeps its local data, non-HDFS data. And there are 3 directories in there: file cache, user cache, and the NM private one. So you can see the sizes, the size range for the files, and the number of files. So if the user cache contains, tens of thousands of small files. So it does make sense to put this type of data onto GP2 and not ST1. And the added benefit is actually, if you're using HDFS encryption like us, we can just LUX encrypt that entire GP2 200 gigabyte volume instead of the 10 terabyte ST volume, because this data really should be encrypted as well. And because if you were to LUX encrypt the ST1 volume, you're adding, LUX encryption over EBS encryption plus the HDFS encryption on itself, and that's kind of a low-performing recipe. So here's an example of a script that I used to just GPT partition and align these large EBS drives. So this is an excerpt from a larger script. There's no warranty on it, so use it as you may. The important point here is that when you're deploying a cluster, you can specify the location of HDFS, Yarn, Impala. Just don't put them under the same directory. Put them under, usually it's under HDFS, and here the nomenclature is 1 for the first ST drive to 4, and then we have the DFS folder for HDFS, Yarn for Yarn data, Impala. If you were to put that Yarn and Impala data in DFS, when you reboot the system, first of all, you're gonna have to change the permissions in order for Yarn to read that because it's owned by HDFS, and that's kind of a security violation. And then when you reboot the system, it's gonna change back because the Cloudera Manager agent keeps all that in sync. And you'll just all of a sudden have HDFS data but not be able to run jobs and whatnot. And of course, anything over 2 terabytes has to be GPT partitioned. Align it on the 2048 byte, okay? So improperly, so these are virtual drives. If you're not aligning the volumes, then you'll have lower disk performance, okay? And with this script, I just automatically detect and partition and set the FS tab just automatically. This should be run as user data. This could be pulled as part of a Cloud Init script. In fact, I actually configure everything, well, as much as I can by convention, because it's just easier that way. What do I mean by that? For instance, we have one Etsy FS tab that governs all these instances, whether it's an RCO server or a worker node or a master node or a SaaS foundation server or gateway. And it's just the way I label it that you can sort of utilize. And we'll get into that a bit. So putting it all together, I have a sort of it's non-scientific. It was hard to get the data, but we have an old cluster that runs RHEL6. There's no hybrid SD1 GP2 layout. There's no kernel C-state tuning. You still use a CMS garbage collector. And we have a more modern Red Hat 7. So you need a 310 kernel or higher. We use a hybrid SD1 GP2 layout. We've got C-state tuning. We use G1GC. And even though, actually I left this out, but System B actually is a smaller instance type, but that's not really all that important because, like I said, R4 4XLs, 8XLs, 16XLs, they scale linearly. As long as when you run the jobs, you keep the number of executors the same, it should run about the same. Networking is a bit slower though. System B actually runs 2 to 3 times faster, and garbage collection occurs much less. So I'm going to leave you with just a simple, one of the major things that we have to do is to elastically expand the cluster. Now this cluster is Kerberized. It's got TLS 1.2, and if you are familiar with Cloudera Hadoop, adding nodes in a TLS 1.2 cluster where both the Cloudera Manager and the agents are checking certs requires you to sort of disable TLS 1.2. That's not going to happen. We can't do that. And we can't reboot CM, because then we'll cut out on monitoring. And in our environment, because we're still transitioning into the cloud, we don't use Route 53 or any of the directory services in AWS. So all these nodes, all this Kerberization occurs via AD clusters on-prem. So what we do is we pre-compile all the nodes, and we get them all set up so that they are Kerberized and joined and whatnot. You pre-generate the SSL certs. So we're using a sort of a private, it's a private hybrid cloud system. So you can pre-generate the key stores and the certs for every single server, even if they don't exist, and then load up the Java key stores so that Cloudera Manager, when it boots, will have all these certs in memory. We use convention to name the certs. There's no specific host name that's in any of these configs. And we put the config file in S3. It's part of our init process. So if you're familiar with Cloudera Hadoop, there is an agent running, and the agent uses a config file under etc Cloudera SCM agent called config ini. And in it, in order to have a TLS cluster, there are these 4 parameters that need to be specified. One is the private server key, public server cert, use TLS equals 1. And because we're security conscious, we don't generate server certs that are passwordless. So Cloudera Manager, Cloudera Agent has the ability to use a command like cat to read the password for that particular server key. And that key, that password file sits on our servers. It's root readable only. So basically, if you're on the server and you're root, you pretty much own the box. So it's change POS expressions 400. So you can use this command, and because the agent runs as root, you can cat the password in order to initialize the agent or start it. And so what we do is we use user data or CloudFormation to install the daemons or agents RPM. And what this does, so the RPM from Cloudera actually overwrites that config igni instead of saving the new config as an RPM-new. So that's kind of an issue. So what we do after that is we pull down the config igni from S3, and then we just restart the Cloudera SCM agent. And what that does is immediately the agent communicates with Cloudera Manager, and it's already become a managed box. And then what you can do is you can use the CM REST API or go directly to the GUI and apply a config role. A config role is just basically a set of services that you've defined as the gateway, the worker, and whatnot, and that initializes the node. So it works for us. It works really well. We were able to expand a cluster from 20 nodes to dozens and dozens within 24 hours in a sort of like an enterprise environment. Like if we were able to do this with AD, like AWS AD or Route 53, it would be much better. It would be faster, but we have to work with what we have. So in summary, I think the take-home points are we really have to understand the workload and match its storage, performance, pricing. For HDFS, had we used GP2, we'd have paid $80,000 per month instead of $36,000, based upon the numbers I showed in the beginning. Had we used all SC1 instead of ST. So S3, I didn't talk too much about it, but it is sort of a backbone for a lot of our data. So we keep a lot of the write once, read many time data in S3, and that saves us, extra $25,000 a month. We use optimal EC2 types. We tune our AMI, or use, if you can, the AWS AMI. We use S3 to share and distribute the data, and if you keep up with CDH, you'll get the benefits of the improvements, things like fast upload for S3, S3 Guard, which provides the DynamoDB back consistency check for actually enabling transactional workloads on S3 via Cloudera. Like I said, you need to be on CDH 5.11 and above for that. Thank you all for attending. I hope this was helpful.
So if you would like to learn more about EBS, we have a number of EBS sessions this week, all different types. There are chalk talks and deep dives. So there's just a sample here, also available in the app to find the ones that may interest you on leveraging EBS. So with that, I would like to thank Alex and Experian for the time and sharing their story with us. Very interesting how they leverage different types of EBS storage and how they built in their clusters and how they get the right performance and cost benefits out of that. So thank you, everybody. Really appreciate your time and hope you enjoyed the session.